Hello all. Today we're going to talk about earthquakes and mountain building. So we have already talked about plate tectonics and we've already talked about volcanic activity, and both of those things are often associated with earthquakes, but we haven't had the opportunity to talk about these in specific detail. So that's the focus of today's lecture. So what is an earthquake? An earthquake is a vibration in the earth that's caused by a sudden breaking, slipping, or some movement of the solid earth surface. And you guys have likely seen images like I have on the bottom right here that are created by seismometers, where you can see that the straight line at the beginning of the diagram indicates that the surface of the earth is not moving, and then all of a sudden the surface of the ground starts moving up and down, and that is recorded as a particular earthquake event on this chart here. So earthquakes can occur for a variety of reasons. Sometimes they occur because there's movement along faults, which are large fractures in rock, where the rock on either side is moving in different directions, and these may be places where two plates are converging, meeting one another, or diverging, but they can also occur on the interior of plates as well. In addition, maybe there's magma that's moving up underneath a volcano, and that is causing a movement of the overlying rock that could initiate an earthquake. A volcanic eruption, where there's a very dramatic movement of lava out of the interior of a volcano spilling out onto the ground, could cause rapid vibrations of the ground. But also other large things like big landslides can initiate earthquakes, and even human activity can initiate earthquakes, like large nuclear tests or even smaller disturbances can create very small sized earthquakes. So a lot of different things can create earthquakes, but a lot of the major earthquakes that we think about are associated with different kinds of plate movement. So if we look at a map of where earthquakes occur around the planet, we can see this image here where the different dots represent earthquake activity. And this image almost looks like a map of the plates. You can pick out the African plate kind of in the middle of the slide, South American plate, North American plate, Eurasian plate, etc., etc. And that's because, as I just mentioned, a lot of the earthquake activity occurs along these plate boundaries. But you can also see that there are earthquakes that occur on the interior of plates as well, and there's a variety of reasons why we might have faults or different volcanic activity, hotspots, and other things in the interior of plates that could initiate earthquakes as well. So, as we said, often it's this movement along plate boundaries that is initiating earthquake activity. And in order to understand how this works, we want to understand a little bit more about how plates move. And in order to understand that, we need to know that plates move a little bit differently in the interior of plates compared to along the exterior of plates, where the plates are coming in contact with an adjacent different plate. And so geologists have different terms that they use to describe these different types of motion. And the first type of motion is called far field motion. So far field motion is the kind of motion that occurs out in the interior of the plate, far away from the plate boundary. And this kind of motion is actually quite slow and steady. It's very consistent over time. So if we think about average plate motion of a certain plate being 2 centimeters a year or 3 centimeters a year or faster for certain plates, and we went out to the middle of the plate and located a GPS sensor on the plate, we would actually find that each year and throughout the year, the slow and steady motion is actually really quite consistent. However, that's different than what we would see in the near field motion. So near field motion, remember, or don't remember, know is motion that occurs along plate boundaries. So this is on the exterior of plates where one plate is meeting another. And compared to far field motion, this motion is very inconsistent. So this motion may be very still or very stagnant for years or decades at a time. And then there might be an event where there's very fast, rapid motion all at once. And when that fast, rapid motion occurs, we often experience an earthquake as all that energy that's been built up is released. So we have this picture down here of this gentleman with the world record fingernail length. And remember, this is about the average speed that plates are moving, the same speed that your fingernails grow. So that's a couple centimeters a year. That's what we would find in far field motion out in the middle of plates. But if we came to the exterior of the plates, we would experience near field motion where there might be no accumulation of plate distance for decades at a time, and then all of a sudden we might have movement of a plate of many feet or many meters in a matter of a few seconds. So a lot faster than your fingernails grow. Okay, so this kind of brings us to the theory of how earthquakes actually happen, and this is described by geologists as elastic rebound theory. And elastic rebound theory goes like this. Rocks at the plate boundaries experience friction. So friction is a force that's pushing in an opposite direction of motion. So as one plate is trying to move in a certain direction, it's bumping against another plate, and that plate is pushing back against the plate and preventing it from moving forward. However, as the rocks along the boundaries get stuck, the rocks out in the middle of the plate continue to move. And in order to accommodate this difference in the rate of motion, there's actually a slight elasticity built into rocks. So we think of rocks as being very rigid, right? They don't seem rubbery. They don't stretch and snap back into place like a rubber band. But there is a slight elasticity to this material that allows a little bit of stretching so that one part of a rock can actually be moving a little bit faster than another part of the rock. However, this elasticity isn't infinite, and so at some point the elasticity of this rock material will be overwhelmed. And when this happens, the rock snaps back into place. So usually the rock that was being held in place by the friction snaps forward to catch up with the rest of the rock that moved on without it. So that process is called elastic rebound. That explains what's going on when earthquakes occur, and again, we call this elastic rebound theory. So here are some different images about how these rocks might be offset from each other. So first of all, we could have one rock that's kind of moving laterally compared to another rock, and then the part of the rock that was stuck with friction can snap forward to catch up with the rest of the rock. Also, sometimes this displacement that's occurring is vertical, so part of a rock will be pulled vertically away from another part of the rock, and then the rest of the rock will snap forward to create more consistency, or will allow the back part of the rock to catch up with the upper part of the rock. So we have different names for these different kinds of faults. Strike-slip faults occur to faults where we have this horizontal or lateral displacement. Reverse faults and normal faults refer to the kind of faults that occur when there's vertical displacement. And if you want to learn more about that, you can take geology. So one thing that's particularly interesting about earthquakes is that over time they can actually create really dramatic geologic structures. So far we talked about how volcanoes can be built on the landscape, and we talked about different volcanic processes creating different types of mountains with different shapes and different sizes. But mountains can actually be built by earthquake activity as well. And the name orogenesis refers to this mountain building process. So if we have many incidents over centuries or millennia of this vertical displacement occurring where one rock is being pushed up above another rock, then over time that can add up to these really dramatic geologic features where we have big mountains and steep-sided cliffs that are extending way up above the landscape, above features below. So this is something that we have been experiencing along the eastern Sierra for many millions of years. So the Genoa Fault Scarp, which is a little bit south of Carson City, is something that maybe some of you have seen before or would have the opportunity to see because it's fairly close by. And we've had relatively recent, in the last 100 years or so, earthquakes in this area that have exposed a lot of vertical wall of rock, and it kind of illustrates how this is happening again many times over centuries and millennia. We can get these big steep-sided mountains like we see along the east side of the Sierra. The Rocky Mountains are also in many cases built by this kind of earthquake activity that has created a lot of vertical displacement over time. So here's an image of the Flatirons, which is kind of part of the Rocky Mountain range outside Boulder, Colorado, and you can kind of see how this rock is sticking up out of the landscape, and it's sticking up because of past earthquake activity. In particular, somewhat locally, we have a lot of landscapes that fall into a category that geologists call horse and graben landscapes. So horse and graben is a German word that refers to these kind of rises and graves on the landscape. And in this case, these alternating mountains and valleys are created along fault lines where we have certain blocks of the lithosphere that are sinking down into the ground, and then alternating blocks next door that are being pushed up or being left up as the other pieces are falling down below. And this is the kind of thing that we see all through Nevada, Arizona, parts of eastern California, Utah, in the area that we call the Basin and Range, or kind of the Great Basin area, where we have all these alternating mountain ranges interspersed with flat valleys, followed by another mountain range, followed by another valley. If you've driven around in Nevada, you know that this is a familiar landscape. And these are created, again, by earthquake activity that are creating displacement between the vertical pieces and the horizontal pieces below. So, in addition to earthquakes being exciting and potentially dangerous geologic phenomenon that can create problems for humans around the world, they're also really important processes that actually create the landscapes that we see around us today. So important for geologists to understand in lots of different kinds of aspects. All right, that's what I have for you guys about earthquakes today. Have a nice afternoon.